Let's look at some simple probability examples. Here we have a fair die being rolled, and we want to find the probability that you get a 1, 2, or a 3. Or excuse me, just a 1 or a 3. The first thing that I would want to do is make sure that I understand what the sample space is. For a fair die roll, the sample space consists of the possible outcomes, which are the numbers 1 through 6. What we're looking for, we might call it the event E, is getting either a 1 or a 3. If you phrase it this way, you can see that the basic probability principle applies, which says that the probability of an event E is the number of ways that E can occur divided by the number of elements in the sample space. Here, of course, a 1 or a 3, if you count in your sample space, that's 2 ways that can happen, and there are 6 elements in the sample space. So the probability of getting a 1 or a 3 is 1/3. I could also ask, for instance, the probability that you get a 7. Well, the probability you get a 7, since 7 is not even in the sample space, the probability of a 7 is 0 because that's an impossible event. Another example. Suppose we have a card being drawn from an ordinary deck of 52 cards. We want to find the probability of drawing a red card or a face card. Now, in order to do that, you've got to know something about cards, and here's some important things that are going to come to bear on this. First thing I would say is that half of the cards, half of 52 is 26. 26 of those cards are red. I also know that the face cards are the jacks, queens, and kings. There are 4 jacks, 4 kings, and 4 queens. So 12 of those cards, and again, like I said, there are 4 kings, 4 queens, and 4 jacks, are face cards. And the other important piece of information is that some of the cards are red and face cards. In fact, half of those 4 kings, half of the 4 queens, and half the 4 jacks, in other words 2, 2, and 2, are actually red face cards. So I would say 6 cards, half of the kings, half of the queens, and half of the jacks are red and face cards. And the reason I'm phrasing it this way is because I want to apply the union rule for probabilities to calculate this. The union rule, and I'm not going to write down the whole thing, the union rule for probability says that if you've got 2 events, and I'll call them here F for face card and R for red, if you have the probability of the union of 2 events, that's the probability of one of the events plus the probability of the other event, and then you've got to subtract off the probability of the intersection of those 2 events. Here F stands for being a face card, R stands for being a red card. Well, the probability of being a face card, if there are 12 face cards out of a deck of 52, then that probability is 12 50-seconds. There are 26 cards that are red, so the probability of being red is 26 out of 52. And the probability of being red and a face card, well, there are 6 of those, so that would be 6 50-seconds. And of course, 12 plus 26 is 38, minus 6 is 32. So you would have a probability of 32 50-seconds that you would have a red face card. And of course, you would probably want to reduce that, and if you did reduce that, that would reduce to 8/13. How about another one? Let's go back to the fair die being rolled twice. I want to know here, what is the probability that the sum of the two rolls is 7 or the first roll is a 2? In other words, what I'm really looking at is something like this. The probability that the sum is 7 or, which is a union, the first row is exactly 2. Now that is a problem for the union rule again. The union rule says that the sum of the probability of the union of two events is the probability of the first one, which is the probability that the sum is 7, plus the probability of the second one, which is the probability that the first row is a 2, minus the probability of the intersection. In other words, the probability that the sum is 7 intersected with the probability that the first one is a 2. Now, what is the probability that the sum is 7? Well, if you look over here at our rectangular array that allows us to look at this in a logical way, the sum being 7 are all the elements on this main diagonal. In other words, 1, 2, 3, 4, 5, 6 of them. So the probability that the sum is 7 is 6 out of 36. What about the probability that the first one is 2? Well, the first row is indicated by the first position. The first row being 2 is here, and that happens also to be 6. 1, 2, 3, 4, 5, 6. So that also happens to be 6/36. And then I've got to subtract off the probability that the sum is 7 and the first one is 2. Well, you can see from the overlapping areas that there's only one row combination that has a first element of 2 and a sum of 7, and that says 2, 5 right here. So there is a probability of 1 out of 36 on that. And so you've got 6 plus 6 is 12, minus 1 is 11/36, is the probability of having either a sum of 7 or the first row being 2. Let's do one more. Here we've got an example that says, this table shows the probabilities of a person having specific amounts of credit card charges in a 1-year period. And I want to know what the probability is that a person has 2,000 or more in charges during this period. Well, if you look at the table, the 2,000 or more would encompass these two categories. Now the trick here is to notice that these two categories are mutually exclusive. You can't be between the range of 2,000 and 499 and 5,000 and over at the same time. So because these categories are mutually exclusive, I can calculate the probability of being in the category 2,000 or more simply by adding up the probabilities of being in either category. And I can do that because the categories are mutually exclusive. So the probability would simply be 0.13 plus 0.07, which happens to be 0.20 or just 0.2. So the probability that a person has 2,000 or more in charges is 0.2.